Okay, 2016, day 17. Let's get set up for that. And then this 17, day 17. Try to build it. It fails to build. Create the file. Go to the file. 2016, day 17, build. Oops. There we go. Nice. I'm just doing that just to see if Ultisnips remembered after flipping out of the buffer, but it didn't remember, so that's good news. Okay, so we have day 17 is unsolved. Let's see what it is. 2 steps forward. You're trying to access a secure vault protected by a 4x4 grid of small rooms connected by doors. You start in the top left room, marked S, and you can access the vault, marked V, once you reach the bottom right room. Scuba Craving says, you're really good at this. Thank you. I lucked out with a very easy puzzle to start out with, so there wasn't any trick to it. This one looks like it's going to be a maze searching algorithm, which means maybe we can leverage our Dijkstra. So let's see. Fixed walls are marked with a hash and doors are marked with a dash or a vertical bar. The doors in your current room are either open or closed and locked based on the hexadecimal MD5 hash of the passcode, your puzzle input, followed by a sequence of uppercase characters representing the path you have taken so far. Yeah, MD5 seems to be the theme this year, right? RG MD5. Oh, okay. So it was used in 3 other puzzles, and now this is the 4th puzzle it's being used in. Okay. Followed by a sequence of uppercase characters representing the path you have taken so far. U for up, D for down, L for left, and R for right. Only the first 4 characters of the hash are used. They represent, respectively, the doors up, down, left, and right from your current position. Okay, so any B, C, D, E, or F means that the corresponding door is open. Any other character, any number, or A means that the corresponding door is closed and locked. To access the vault, all you need to do is reach the bottom right room. Reaching this room opens the vault and all doors in the maze. Okay, that's convenient. All right, for example, suppose the passcode is HIJKL. Initially, you have taken no steps, so your path is empty. You simply find the MD5 hash of HIJKL alone. The first 4 characters of this hash are CED9, which indicate that up is open, down is open, left is open, and right is closed and locked. Because you start in the top left corner, there are no up or left doors to be open, so your only choice is down. Okay. Next, having gone only 1 step, down or D, you find the hash of HIJKLD. Okay, so as you work on... Okay, yeah, and then going right means hashing HIJKLDR. And then you look at the first 4 characters of... Only the first 4 characters of the hash are used. This produces F to be C, which indicates you can go back up, left, but that's a wall, or right. Going right means hashing this to get this. All doors closed and locked. Oh, okay. So once you enter the room, if you start at the top of the maze, you go down then right, then the result is that every single door is closed and locked. So you can't go that way. So you back up. Going up instead is worthwhile. Even though it returns you to the room you started in, your path would then be DU, opening a different set of doors. DU opens a different set of doors. After going DU and the hashing HIJKLDU, only the right door is open. After going DUR, all doors lock. Fortunately, your actual passcode is not HIJKL. Oh, okay. So this is a good way to at least test our algorithm. All right. I guess what would be the an approach would be to just work our way through the maze. What is our input here? Okay. Should I just do that again? Const puzzle input is this. Right. So there's no parsing to do. So part one is, you know what we could use, and maybe this is a good opportunity to do this. We wrote a Dijkstra search. And the whole point of doing this AOC stuff anyway is to generate a library of. So let's save out of that. That should still build, even though we have a warning about not using the puzzle input. In our source, we have this library, right? But we also did Dijkstra, RGDIJKSTRA, right? Yeah. So in day 11, we did a Dijkstra search. So let me move this. This will be like 17A, day 17, part 0 is getting Dijkstra to be a generic routine. Let's work on that. So copy this, and we'll call this source search. And then edit this, and we're going to blow away everything except for the Dijkstra code. Where's the Dijkstra code? Here it is. I even put little handy comments around it to show that this is a separate thing. And then instead of the Dijkstra search on building, we want to actually have it on just a random type trait, which implements two functions, right? We want to be able to get the moves, and we want to say, is it a winning state? Those are the two functions we need. Search, called that, and then fn moves of self returns. Okay. What do we want to do there? Because we want to have it return a vector of moves. Yeah, so this is a vec of self, whatever self is. And we might have to put a little clause on that. Let's see, and then is win. Let's call it win state self, and that returns a bool. And then this just takes this type T, which is a Dijkstra search. So we can say T. Like that. And there probably has to be something else there because we have to be able to clone it. So let me add clone to that. Oops. Clone. And now all the word buildings change to T. Oh, that means it also has to be hashable. Right? Clone, search plus clone plus hash. And then I got to add it to the library. Mod search, pub use search star. And then in our day 11, we'll say use AOC lib dijkstra search. And then dijk. So instead of doing this, we say we need to make building. We have to implement the Dijkstra search on building, which we've already done. We just need to move the code to it. Impl dijkstra search for building, and then we just need to move the moves, these two traits, right? Moves and is win state. Fn moves. So we can grab all of this, right? And put that in the impl. like that. And then isWin, fn isWin. So all of this as well. Yeah. State. Right? I think that's all we need to do there. And I've already done those things there. So is that all we need to do? No. Oh, right. All of our tests need to be fixed. And the function calls need to be fixed because it's no longer Dijkstra search. It's actually b.search. Oh, no, it's Dijkstra search of B. Yeah. Okay. All right, let's see what blows up. Everything. Hash is not a trait? Sure it is. Core hash, standard hash. Let's use that one. Like that. And what else is going wrong? Cannot find type hash set. Okay. So let's pull that in. Use standard collections. And I use hash set and hash map. So let's pull them both in at the same time. What else is messed up? Hash map, right? All right, so it looks like it's all going to be those. Vex self doesn't have a size known, right? So we have to say something like where self sized. Oh, and it formats it down there. Okay. And now we don't have insert. Following trait bounds were not satisfied. EQ. Okay, we can add that. So EQ plus hash. And then isWin state. Dijkstra search is not. Oh, I have to make it a pub trait. And this has to be a pub function. And then this is isWin state. Oh. What is this? Oh, I left it in here. Okay. I thought I deleted it. Let's delete all of this from day 11. All right. Not found in the scope. Oh, okay. Okay. Oh, now day 11 doesn't use hash map or hash set. Okay. Does it use hash and hasher? Oh, it does. Oh, maybe it just doesn't use hash map, just hash set. Let's find out. We do have two warnings, but that's from the other one. Okay, so let's do this. Cargo test 1611. Okay, so all the tests still pass for that day, which is great. So that means we successfully refactored our search code. So let's add day 11, the library. We'll add search. Yeah, and that should be git commit -m refactored search to the library. Let's call it Dijkstra search because we might want to do an A* search. And we probably should also clean it up a bit. Because you can do this better, this part of it better with a, the binary heap. And I just need to think about how to do that. Okay, so that, right. No, was it no verify? There. So now we just have those. Okay. Okay. So let's go back to 2016 day 16 and use that now. We can say use AOC lib star. Sure. Oh, that's the wrong one. We're on 17. Underscore 17. Oh. Oh, it's not checked in yet. So it's not going to show up in my thing. Okay, here we go. So now here we say use AOC lib star. Okay, so what we need to do is come up with, and we're going to need the MD5. Crate gets sorted before AOC lib. Interesting. Okay. Let's just first see if we can do this. We have HIJKL, and let's just say println this of MD5 compute on HIJKL. And let's see if we see that. Digest cannot be formatted with the default formatter. Yeah, computing. There it is. CED9. Okay, so and I think that's what we were looking for. Yep, CED9. Perfect. Okay, so we're able to see this. Oh, wait a minute. We want to format this with X, :X, right? Yeah. Because debug output is not a... Okay. So that means we can now implement... Let's create a maze, a vault searcher. Struct. Let's do that down here. Struct vault. And it's going to have a, what is this called? Passcode. Passcode of a string. So what we do is now say create let vault equals vault new HIJKL. And then we say impl vault. So we need the new function first, fn new. Passcode string stir, make it easier. Return self, generates a self of passcode to string. And now we want to say impl dijkstra search for vault. And we have to come up with moves of self, returning a vec of vault. For now, we'll just say vec new, because I want to see if it works. And then fn is win state, and bool, and just return false. And then we just have to generate the moves and determine if we've won. And win state, it should be straightforward. Oh, we need our location as well. Right? We need to keep track of not just the passcode, but the string that we're working on. So the path that we're walking our way through, up, down, left, right, and so on. And then our current location, which can just be usize. And then is win state is self location is equal to, and we'll call this 0, 0. Then we just call that 3, 3. Right? That's the win state. We're missing path, and location will start at 0, 0. Okay. Very good. And it built, and we're not using half the stuff. Good. So let's start using it. So what we can do now is actually say vault Dijkstra search on vault. And we can actually just print that out. But we can debug things along the way and print out our current moves, right? So println considering, and then what we can do is just derive debug. On that. Right, and then that way we can see, it should say considering HIJKL, and then return that as a move. And we'll compute MD5 on that. So it doesn't like something there. Trait clone is not implemented for default. Okay. Oh, and then we also have to derive all the other guys, right? EQ and hash. Partial, EQ, EQ, and hash. Okay, so it did. And then option unwrap none value. Right, so we're assuming that there's going to be something there, I guess. I don't know. Let's take a look at search line 73 and see what that's trying to do. Oh, it's assuming that there's a path. It's assuming that there's a path. Why don't we change that then? Why don't we make that an option? Oh, you know what we could do? If we make this return an option of a vault and a use size, we'd be able to see the final state. Right? Because we're going to need that, right? What's the shortest path? The actual path, not just the length. So we'll need the final result. So yeah, let's do it that way. And if we return an option, we can go down here and say, if target is none, we can just return none directly. I think that might be, and if that means we have to change day 11 also. Okay. The other thing we can do, I think we don't need the whole path, right? I mean the prev things, I think we can get rid of those because we're not, if we just return the dist instead, let's just comment them out for now. That way we can say return, oh, if target is none, let's ignore it. So it can say let target is equal to target, question mark. And that will return none if target is none. But if it exists, we can return some target clone, right? And then dist get target. And that should do that. And then we just need to fix up. What's the problem? Oh, ampersand. And that's an option. Oh, we can just have that also return none star. There. And now here we need to fix this and say dot 1 for the distance. Oh, unwrap dot 1. And the same thing here, unwrap dot 1. Because we don't care about the path. Unwrap dot 0 dot path. Yeah, path. So that'll print out the path. Okay. And it's still panicking on line but now it's unpanicking on line 24 here because we don't have a path. We're assuming that there's a path, and right now there isn't one. So we get a none on this unwrap, and we fail. All right, that's good. But we do see considering here. Oh, I need to fix a test. Cargo test 11. And these will all fail. Yeah. So let me fix those two, since otherwise I'll forget, and then I'll be very annoyed. So unwrap .1. So it's just those two. Yes. Okay. Git status, git add source search, and this guy, git commit, return state and distance for Dijkstra search. No verify. Okay, and then I can say git show head. We can see what we did. All I did was change all those to unwraps. I changed this to an option. I comment out the prev thing because we're no longer using it. And then we just return the distance. Perfect. Let's go back here. So many things. Okay, so I think now we're set up to return the path, which is what we care about. So now we just need to generate moves. How hard could that be? So we need to come up with a result vector, which contains all the moves, and we'll return that. I still want to print out considering because I want to see them all. The current path is going to be the passcode followed by the whatever's in the current path, followed by an up, down, left, or right. But it's dependent on whatever the current path's MD5 hash generates. So we can say let digest is equal to format bang. Right, we're going to extract it as a hash, compute format bang, the passcode followed by the path. And that's going to be a string, and we just care about the first 4 characters. So we can say dot chars dot take 4, right? And that's a take. Okay, so then we have to actually iter next, right? We can say let up char is equal to digest next unwrap. That's a char. And we can say if self.location of the x coordinate. Are we doing x or y first? Oh, this is up. Right, so we care about, well, I guess maybe we can make this row column. Let me put a comment here saying this is row column. Oops. Row column. So if the row is greater than 0, which means we can move up, and up char, oh, can we say greater than or equal to b? I think we can. Right, it was B, C, D, E, or F, and that's all it's going to be. Then our next move, result.push, is going to be a vault containing the same passcode. So we're cloning those all over the place, but we need the whole thing anyway. A new path, which is going to be format bang, the current path followed by u. And then our location is going to be lock.0 minus 1, comma lock.1. Doesn't like that. And it doesn't like this. Oh, self. And it doesn't like this. Can't buy or digest as mutable. Temporary value. Oh, dang it. So we can't do it this way. Okay, collect. Back char. That'll force it to be a, and we don't need it to be mutable. It's a vec of char, and then we can just say digest of 0. Okay, that builds. And now we just need to do one for each of the remaining directions. 2, 3, and 4. So the next one is, it's up, down, left, right for the 4 things. So a digest of 1 is going to be down, which means lock 0 has to be less than 3, right? And then this becomes left, lock 1. Can we move left, which means that has to be greater than 0. And then this changes to 3, and this changes to 1, and this is less than, and that's 3. Oh, and then we have to change the letters. Up, down, left, and right. And then this is +1 here. And then this becomes -1 here. And this becomes +1. Like that. And then that's our resulting moves. Right, so now each direction has its own move. And we add that to the result array, and then we can see if there's a win state. And now we can see I'm running tests, but there's no tests. So let's just hit run. Oh, I didn't save it. Okay, let's save it. And then we should see it considering more moves. And it should still panic because it can't find it. Yeah, so it found it. HJKL has a DUR, right? That was the longest distance we could go. You have to go DUR, all doors locked. Fortunately, your actual passcode is not that. All right. So I think it's working. Let me take out the considering because I don't know how much output this is going to generate. And then let's use it for real here with puzzle input. Oh, came up with an answer. Is it right? Let's find out. Oh, that's the right answer. Okay, so Dijkstra solves our puzzle once again. All right. Is there anything we can do to clean this up? I mean, this is standard move stuff, so there's not much you can do about that to make that cleaner, right? I don't know what else. And this is just this. The only thing I can think of is that maybe we generate the vault in the parse function instead. And then just use it as a self vault. But let's see what part 2 is before we optimize that. Git status. Git add source. Git commit -m 2016 day 17 part 1. Done. All right, part 2. Let's crush this. You're curious how robust this security solution really is, and so you decide to find longer and longer paths which still provide access to the vault. Remember that the paths always end the first time they reach the bottom right room, that is, they can never pass through it, only end in it. For example, if your passcode were blech, the longest path would take 370 steps. With this one, it would be 492, and for this one, it would be 830. Okay. So this is crying, and now that we have actually test cases, oh, I could have written test cases for those too. I totally ignored that. Totally ignored that. Okay. Maybe we should throw those test cases in. But it's part of the vault, I guess. I don't know. Yeah, we can do that, right? We can still do a test. part1, 1. We can insert equal that vault new of this is equal to dot unwrap dot 0 dot path is equal to this to string. Can we do that? And switch this over to test. Oh, vault new. Oh, right. We have to do it in 2 steps. Let vault equals this. And then we say Dijkstra search vault. Yeah, okay, that, oh, it's testing the wrong thing. Okay, we have to edit our bacon init. Oh, bacon toml. Tests. 16 changes to 17. There we go. Bacon. Okay, test part 1.1. Let's just throw the other ones in there, just for completeness. Test part 1.2. Let vault is equal to vault new. And then, sort equal Dijkstra search vault unwrap 0 dot path. I could just copy pasted, and then this is going to be this thing here. What did I do wrong? Oh, fault. That's my fault. Kafka says searching for the fault. Yeah, I found it. I also have a typo. Dijkstra search. Search or search? I'm going too fast. And then part 1.3. Hello, Kafka. How are you? Part 1.3 is this. And we'll put this one in here. And this. It's a very long one. Let's see if the test goes very fast. Dijkstra is speedy with this code. Okay, even though we're doing those MD5 hashes all over the place. Okay, so part 2. Part 2.1. I'm going to say let vault is equal to the same one up here. And then we're going to have a different function, right? Because now we're not trying to find shortest path. We're trying to find longest path. So let's just create a function called longest. Oh, I'm doing this backwards again, expected versus actual. So we can just say 370 for expected, and then we say longest path for vault. Almost had a fault there again. And then this should fail because we don't have longest path. So let's write longest path. The vault returns usize, I guess, and for now we just do 0, so we get it to compile and the test to fail. Good. All right, so the longest path. How do we want to do this? We want to look at each location and then see if we can go from there, right? And then just add. So it's similar to like maybe a flood fill, where we put on a new. We have a stack basically of places to visit, and we keep visiting new places until we run out of places to visit, and then that should give us a longest path, right? So if we say longest is equal to 0, and we have a stack is equal to vec new, Actually, we want to push on our current, whatever our current path is, which is just going to be vec bang vault v. Oh, v.clone, because we want them to actually be vaults, not references to vaults. And then we say while not stack is empty. We get the next state in our stack, right? And then for m in state moves, we get the moves from the trait that we already have, and that should be a vault. It is. Do we want to have to check each location to make sure we're not revisiting? So h is hash set new. So we'll create a hash set of all the places we've already visited. Let's call it visited. If visited contains m, then we continue. Otherwise, we visited insert m clone and say stack push m clone, right? Because now we want to consider that move next. But if it's an end state, we can do that up here, right? If m dot is win state is what I called it. So then the longest is going to be longest dot max of m dot path dot len, right? And then we don't want to go anymore, right? So if it's a win state, then we grab the longest. If it's not the win state, and continue. If we visited already, actually, should that go up here? And then otherwise we stack push, and then we can just print, return the longest. Is that all we need to do? We don't have a hash set. Okay. It worked. Okay. It worked. That's good news. Is it true? Okay, first of all, I see one thing we can make better. We can say let some state is equal to stack pop, while let some state is equal to stack pop. That's one thing we can clean up. But I think it's true that we never visit the same place twice, right? Which means, because every time we generate moves, it's going to be one level longer. And even though we're visiting the same location in the maze, it's going to be through a different path each time. So I don't think we need visited. Let's take it out and see. Yeah, we don't need visited. Okay, so that simplifies the code even more, right? If we have a win state, we got a win state, and then we can just change this to an else. And that should still work. Yeah. That works. Okay, let's just make sure it works for the other two. Part 2.2. And it's this thing here. And we're going to say, what are we expecting this to be? 492. 492, longest path of vault. And see if that passes. It does? Okay, so I think we should be confident, but I'm going to put this one in here anyway. Part 2, 3. And then we just do this. And this should be 8:30. And we still have a warning. I don't see the warning though. Oh, because we're not using longest path in the real thing. Okay, so now let's use longest path in part 2. Right, so this is where we just re-implement this thing here as vault, 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 new of nothing, and then parse becomes this. Oops, I forgot that. Oh, did I forget a closing brace? I did. I also need to change this to self vault, right? The test still pass. If we hit run, it should give us the warning about longest path. And wow, that takes a long time. Oh, to build. It takes a long time to build. Okay. 5 seconds to build, but no time at all to run. And now we can just say longest path of self vault and come up with the answer in 5 seconds. 398. That's the right answer. 1 gold star closer. Nice. So we did 16 and 17 today, and we refactored the Dijkstra search into the library. It is now part of our library of possibilities, which takes this trait object, which generates moves and determines whether things are in a win state, and it also has to have clone, EQ, and hash. And now Dijkstra search doesn't just return a length, but it also returns the final winning state as well as the length. Okay. Git commit -am 2016 day 17 part 2, and you might be able to tell from the cadence of my voice that I need to wrap things up here. Should I peek at 18? No, I'm not going to peek. I'm not going to peek. So tomorrow we'll continue with 18, and if that doesn't take too long, we'll also do 19.